This new syntax is a big improvement over our old syntax, but you can imagine it might be even better. For one thing, we're having to explicitly mention the store everywhere, and we have to be careful to make sure that we use the right one. In this call to interp, we have to make sure we use the result from the previous interp. If we use stow here, then that would break our interpreter. We're always supposed to use the most recent store. Similarly, we have to make sure that we return stow r here and not one of the previous ones. Both the fact that we have to write this down and the fact that we have to get it right are things that a language might improve for us. It might automatically thread the stow through for us. So what I'm going to show you is a way to transform our program into a syntactic form so that we can use a syntactic form that does that kind of thing. The transformations are not obvious, and in fact it'll seem at first like we're going in the wrong direction, making things more complicated. But as we make it more complicated, we're actually making it more uniform. The first step is to take our interp function, which currently takes 3 arguments and returns a result, so that it instead takes 2 arguments and returns a function that takes the store and returns the result. This is called currying. So instead of taking the stow here, then we will take it as a second argument after all of the others. I would call this new one interp star, and then we could define interp, which takes stow as call interp star on a and env, and then you get back a function that's expecting stow. Then everywhere from the outside we will use interp, but on the inside we'll use interp star. In addition, besides taking stow as second argument, I'm actually going to push this down into all of the cases. Right? So whether we take stow before or after we do the x_c split doesn't really matter, and we get the same type. You see, we take an expression in an environment and we return a function that wants a store and then returns a result in that case, and we have to do this everywhere. Okay. I'm not going to type all of this out now, but if you do type it all out, then you end up with something that looks like this. So here we have interp star. I push the stows all the way through everywhere. And like I said, this doesn't look better. If anything, it looks worse, because instead of interp lm, now we have recursive calls that use interp star and then immediately pass the stow in. What we're doing though, what we're making more uniform and what we're headed towards is pulling stow out separate from everything else so that we can eventually hide it. So our next step is to look at other places where we use stow directly and try to hide those as well. For example, we have stow used directly here. We could do the same kind of thing on v star s as we did with interp. We can make a curried version of it, which I will call return star, which will be a function that takes a value and then takes a store, and then it returns a v cross s of v in store, like that. And then we're going to use return star here instead of v star s. So you'll notice that everything that I'm introducing I'm calling a name with a star on the end. So star is my convention to mean returns a function that takes a store, which then returns some kind of result. v star s is not the only one we have to worry about though. If we look through other parts of the program, we will find new location, for example. It takes a store. Now it may seem strange to curry a function that already has only one argument, but in fact it will make sense to have a new loc star that takes 0 arguments and waits for a store. Still, that won't be quite uniform in the same way as interp and return star, because right now it's returning a single location. So what we will have to do is make all of our star functions uniform, and that they should return a v star s with something and a store. So that new location, for example, returns a v star s the same store, because new location doesn't actually change the store, along with the value that we would have returned before, the new loc. Similarly, override store, which took a cell and a store, now takes them one at a time in the star version, and since its job was just to update the store and not do anything else, we're returning a void value. This may worry you because v star s is supposed to take a value and a store, but I've had to change result. The result type is now a type constructor, where you get to pick alpha, the type that you work on. So where we used to have result, we're going to have result of value because the v is a value. But we can have result of void to be the override store star type, or result of location to be the new loc type. So that's the new curried versions. And if we go now to interp, it looks like this. Okay, it's getting noisier and noisier, it seems, and I promised you that it's supposed to get easier and easier. But we've made everything uniform in the sense that we have these type case patterns with the curried store almost always preceded by a lambda stow. Right? And the ones that are not preceded by a lambda stow, we could convert into that. For example, we could change this to lambda stow v and immediately take the stow v as an argument. Okay. So that's our new lambda, and I'm passing in stow v. Now, as you know, I've got a left-left lambda here, and left-left lambda is not normally useful. Right? It's only something that evolves in evaluation when you think in terms of substitution, or since we're doing syntactic sugar, it might be something that appears in an expansion. And in particular, by doing these kinds of transformations, and then I get to the place where all of my patterns look like this. Lambda stow, type case, some function call that still wants a stow as an extra argument. And then we have a v star s with bindings, and then there's always some other expression that receives that store that we got from evaluating this expression. So I'm going to abbreviate that pattern with a new do form. So the do form is saying do this thing, implicitly passing the store along, get back this value and implicitly a store result, and implicitly pass that store along to this last expression. Meanwhile, we still have return star. So in the case of numc, I have just return star here. It used to be lambda stow return star numvn, that whole thing with stow passed along. But you see, this is the function that takes stow and then calls this part in gray on stow, which is the same thing as just that part in gray, because you're waiting for stow to be passed along. So in the case of the returns, I've simplified that way. Otherwise, I've got this do form where we get the result of interp star with the implicitly passed store gives me value L, then value R comes from interp star R, then we return the result of the number addition. And all of this code then is simplified much more because we don't see the stows anyway, and because of the way the do expands, it's also impossible for us to misuse the stows. We don't know the name that do makes up for that intermediate variable. This could be even a little bit better. You can see that we have do nested. So it might be nice to write do and just a sequence of things, which is our final version here. So in the case of plus c, I have do value left equals that result, value r equals that result, and then finally return. So this do uses a slightly fancier form of macro, where we just say define syntax, and then syntax rules, where we get to have two different possible patterns. If you have a do with an empty set of actions, then you just produce the same thing as result. If you have at least one action, followed by some more clauses, then you expand it in the same way as do one, except where we used to have last, then we have do with the rest of the clauses, and finally some eventual last expression. And for consistently, let's call this last. So that is our most clean version. If you take a step back and look at this, though, all we've done is changed our language so that it looks like we're using imperative features again. This looks like imperatively interpret and accumulate whatever store changes happen to happen there, and then return a value. And that's no accident. What we've done is encoded a syntax for stateful programs, but without using racket state. Is this a better way to program? Well, implicitly we're using state here, so we're writing a stateful program, and that has various drawbacks of stateful programs. On the other hand, it's state that's completely within our control. And some of you may realize that the reason I pick words like do and return is that these correspond to words in Haskell, which has this kind of syntax, something very similar to it, built in, because Haskell has no side effects, and so you always have to do state in this way.